Okay, so we can start off with just taking a look at where we're at for the semester and see if, see what's coming up anyway. So this. Okay, so we are in week 3. We want to talk about section 6 and 7 this week. So on the videos that I posted, I started putting what day I'd like you to watch them by, just to try and be clear about that. That way you don't think that you have to watch the videos for 6 and 7 before Tuesday. Just one section a day is good for the most part. So, so 6 and 7 this week, and of course, if you've already watched the videos for 7 today, you're welcome to ask questions about that as well. You just don't have to feel like you shouldn't feel like you have to have that prepared. So that's for this week. Of course, sections 4 and 5, the homework for those are due today. And let's see here, with 6 and 7 finishing up this week, that is the end of the first unit. So then we'll move on to the second unit next week, and we'll have an exam over the first unit the week after that. So section 6 and 7 homework is due week 4, so week 5 we have the exam for section. The exam will be take home, so it'll be posted on Blackboard, submitted the same way that you submit your homework. I think that's all that I wanted to talk about for now. Are there any questions about content in section 6? Excellent. Any homework questions right away that seem relevant to share with everyone? Or okay. All right. I'll stop sharing that for a moment. And I'm going to go ahead and pause the recording and go grab some sheets that I forgot to grab. So I will be right back. Okay, so what I'd like to do is I'd like to look at the proof of the volume for a pyramid. And I didn't. We of course could have presented that in the content videos, but I didn't really like that idea so much, partly because it just seemed like an excessive number of videos and wasn't really necessary. I'm going to try to just go through this relatively quickly, and if you have any questions, let me know. But if we take a pyramid, and we were to slice it, could make a whole bunch of slices. Then each one of these slices we can think of, right? We can approximate it with a rectangle, or instead of a rectangle, we can think of it as a prism. Each one of these is not a pyramid, but we can approximate it with a prism. So all of the sides would be vertical for our approximation. Oops. All right, so that gives us the idea anyway. So we take a pyramid, slice it. So we slice the pyramid into slabs, as we see here. Then we can let x be the distance from the apex to a given slab. Okay, so if we are looking at this with x being the distance from the apex to a slab, of course, the apex is the top of the pyramid, and then if we were to choose a random slab, this distance would be x. Okay. Also, we would have let's see, this distance here we can think of not as star x. That's not what I want. Delta x. So the slab, the thickness of the slab is delta x. So that way, when we think of if the distance is from the apex to one of the slabs, then we're going to integrate either from the apex to the base or the base to the apex, whichever way you want to think about that. But then we need a way to say, all right, what are our increments of change here? Well, our increments of change are how much we're changing in x. So that's the thickness of a slab. So we can take this and what we have. Well, actually, here, let me add something here a second. I can erase. Get rid of this here and go back to red for a moment. If the overall height is h, then we can find a way of expressing the volume of these slabs. So the shape of each slab is similar to the base. Okay, so if we consider the base, then as we move upwards, each slab is going to be the same shape. They're just getting smaller and smaller and smaller as we move up. So the shape of each slab is similar to the base with a scale factor of SF is equal to x over h. So however far away we are, as we get closer, the distance closer to the apex, the x value is smaller and the h stays the same. So as we get closer to the apex, of course, the scale factor is smaller and smaller. So we have something that's smaller and smaller compared to the base. The area of each slab is the area factor times the area of the base, which would be x over h squared, because the area factor is the scale factor squared, times a. All right, so with that, the slab is, each slab has a thickness of delta x, as we said earlier. So then the volume of each slab, right, which are prisms, is, now each one of these slabs represents the change in volume, because as we add more, we're getting a change in volume. So it represents the change in volume, which is the base times the height, area of the base times the height, so x over h squared times a, the area of the base times the height of the slab. Thus, the volume can be given by the integral of the differential, which is the integral of x over n squared times the area dx. But I have an n squared that I can pull out, 1 over n squared, and the area I can pull out. So this is area over, or sorry, h squared over h squared times the integral of x squared dx. And of course, that would simply be 1/3. In this case, this is a definite integral, so we would be integrating from 0 to h, 0 to h, the height of the pyramid. And so that would be a divided by h squared times the evaluation, 1/3 h, or 1/3 x cubed, evaluated from 0 to h. And because I'm limited on room, we'll just say that evaluates to, skipping a step here, 1/3 a times h. So when I plug in the h, I would end up with 1/3 h cubed. The h's would cancel, and you'd have a times 1/3 h, which is exactly that. When you plug in 0, you'd have 0. Distribute 0. So it's just that. And that's the end of the proof, right? We found the volume to be as was suggested, 1/3 area of the base times the height. There are different ways that you might be able to come up with this. Of course, if you wanted to go back to Calc 2 techniques almost, where you might talk about, well, actually, this lines very well with what's in Calc 2, where you can calculate the volume of an object as the integral of the cross-sectional area. And so the cross-sectional area in this case is exactly that, right? It's based on the area of the base. Okay, so it's the same thing that you would see. All right, and that's the only proof that I wanted to talk about today. The other proof that we skipped over, we'll talk about next week, or not next week, but on Thursday, and that sounds really good to me. If you prefer, I don't. If you prefer that I just record the video, feel free to let me know, but I thought that this would be okay. And then the other thing that I wanted to do was I wanted to just really briefly discuss the homework. So I'm going to open up, let's see here. I can open up this and that works well. So this is sections 2 and 3 that we had that you had submitted last week. So going back to section 2, that's preliminaries to, here we are. The homework was numbers 1, 2, 5, and 6. So for number 1, in this diagram, we're given the measure of angle 1, and we want to find the remaining angle measures. And for the most part, this one was really good. The only thing that was a little bit questionable was, and it was asked during class, and I gave kind of a vague approval to use alternating exterior angles are congruent, which isn't too big of a deal for number 1. But essentially, all that you should be using for this is, well, first of all, use the appropriate language, but then we have vertical angles are congruent. We have several situations of linear pairs, and linear pairs are supplementary, so use that. And then alternating interior angles, since L and M are parallel, and then corresponding angles are congruent because they're parallel. But those are the only things that we really need to use for number 1. I think for the most part that was okay. But make sure that you're being specific about what you're using. So again, many possible different answers, but you could use, you could say that angles 1 and angle 2 form a linear pair, so they're supplementary. Since we know the measure of angle 1 is 112, we know that the measure of angle 2 is 68. I'm okay that you don't necessarily show the equation and solve the equation, because once we know that they're supplementary, that's the detail that we need to be able to find the measure. So that's fine. And then if you wanted to identify 4, you could use a linear pair again with angle 2, or you could use vertical angles with angle 1. So if you use vertical angles, you could say angle 1 and 2 are vertical angles, so they're congruent, and the measure of angle 4 is 112 degrees. So I think, so that gets you all of 1, 2, 3, 4. And then since L and M are parallel, you could immediately just say that, 1, 5, 2, 6, 3, 7, 4, and 8 are all corresponding angles, right? Those pairs are all corresponding angles, which immediately gives you 5, 6, 7, and 8 to make the work relatively short. So that would be perfectly acceptable. But the main thing is right, you don't just find 1 through 4 and then say what 5 through 8 are. You clarify that they're corresponding angles. And I don't think that there was any issue with that. Just making sure that we're being as clear as possible. Yes, okay. So 1, 2, for this one, it was a little bit less clear, not because there were problems that we couldn't overcome, right? We could identify the angles without any issue, but it seemed convenient to also find the values of angles that are not labeled. So in this case, if I could go back, I would say either name them, 8, 9, 10, 11, 12, whatever, or I would say add some vertices, so that way you can name the angles by vertices. So whichever you find best is perfectly fine. I think most everyone labeled them, but that's the best way to go about it, is add the labels to the diagram and refer to the angles. And that way, if those are going to help you find further angle measures. But then again, it's the same collection of tools. Vertical angles, alternating interior are congruent, and linear pairs. That's essentially all that you need to make it through. And okay, so that's that. And 5. For number 5, looking at the diagram, following definition 2.16, explain thoroughly why the following statement is true. If the measure of angle 1 is equal to the measure of angle 8, then the two are parallel. If the angle measure at 1 is equal to the measure at angle 8, then they are parallel. So this is the converse of what everyone had, or what many people had wanted to use, that alternating exterior angles are congruent. So since we're looking at the converse, we need to find a way to justify that L and M are parallel. And this is where I saw a few more issues, or some issues. Some people just swing in a sledgehammer when they just needed a very small tap, tap, tap. That's not as big of a deal, but then we also want to make sure we're clear. So in order to show that L and M are parallel, we can use property 2.17. So in Euclidean geometry, as we are currently working, two lines are parallel, in particular in the figure above, if alternate interior angles are congruent. Now, this is where we want to be careful. It doesn't say and, right? It just has three different things. So each of these can actually be taken individually. Alternate interior angles are congruent. So 3 and 6 are congruent, 4 and 5 are congruent. Corresponding angles are congruent. 1 and 5 are congruent, 2 and 6 are congruent, 4 and 8, 3 and 7. And then interior angles on the same side, transversals are supplementary. So 4 and 6 are supplementary, 3 and 5 are supplementary. And if you were to actually, if you were to take this and assume just one of them, so if alternate interior angles are congruent, so 3 and 6 are congruent, 4 and 5 are congruent, you would actually be able to use supplementary angles and vertical angles to show that corresponding angles are congruent and that the interior angles on the same side of transversals are supplementary. So once you have one of these, no matter which one, you're actually able to show the remaining two. So to show that two lines are parallel, you only have to show that one of these three things is true. So for several students, I guess I shouldn't say several because there's only several of you in here. There were some of you that showed all three. And I think there were also at least one of you that, looking at showing all three as a daunting task, you gave a very vague description of why they were true. So we want to be as specific as possible and as clear as possible in all of our responses. So if you saw, well, I guess just look for the comments that are in the homework, because for this one, there were definitely some comments for some of you on number 5, and then similarly on number 6, because they're similar questions. Yeah, so there's a question about where the comments are in the homework, and I'm not 100% sure on how they show up from the student view. So I'll come take a look and see what there is. So I'll pause this. All right, so I'm gonna, for those of you on Zoom or watching this later rather, I'm gonna try to describe to you what to do because I don't have a student screen here to be able to show you. So when you go to your, presumably grade book, is that right? You go to your grade book and then you click on the assignment that's been graded. It comes up with a window that kind of gives a little bit of a summary, but doesn't actually show you your homework assignment. So if you click on the assignment name, then it will open up a window which has the PDF that you submitted. And on that PDF, you should be able to see any comments that I gave. I give either a check mark or I'll underline something and minus a half or minus whatever, depending on how many points the problem is worth and how big of an issue it is of the mistake. So, but you should see that. In some cases, you'll see, I think it's little boxes that look like comments, or that look like your chat icon on your phone. So I think if you click on those, then it will open up a comment, or maybe they just immediately show up to the right-hand side. And then there's, for some of you in the box on the right-hand side, there will also be some comments. So I put comments in the document, so in what you submit, and I can attach comments to the assignment overall. And sometimes I do both. So make sure that you're looking at the assignment, opening up the PDF, looking at it, and then make sure you're also reading any comments that I gave wherever they show. If you have concerns about this, we can meet on Zoom. I can have you share your screen, and then I can work through you with it. So that's not a problem either. I just need to let me know if you do have any questions. All right, I'll pause for now again and see if I can. Well, actually, I should follow up with some comments about the other homework as well, maybe. So if we go back to here, the section 3 homework, 14, 15, and 16, or 14, 15, and 17 rather. And for 14 here, let me double check, make sure. Okay, excellent. For 14, we're looking at this diagram and we want to find the remaining angle measures. This was another situation where it'd be best if you labeled any angles that you found outside of the angle measures asked for. So the numbers were 1 through 6. I would say that use 7, 8, 9, 10, whatever you need to get there. So for example, let's see, you could find this angle measure here by the fact that this angle and this angle are supplementary, right? They form a linear pair. So that was one that you didn't need to find, but then that allows you to say, well, angle 3 is a corresponding angle, so they have equal measure. And then angle 2 is a vertical angle with 3, so they have equal measure. And now you just got 2 and 3 from finding this 1. Once you have, oh yeah, so that gave you 2, it gives you 2 and 3. For this, at some point, whether it is for the triangle made above or the triangle made below, you're going to have to utilize the fact that the sum of interior angles is 180 degrees. You have to use that at some point. Depending on how you solve it, there's many ways to go there when exactly you're going to use it. And then for this one, for number 15, we wanted to find alpha, beta, and gamma. We're given that beta is 22 degrees larger than alpha. So many of us extended the lines so that way we could use corresponding angles or vertical angles or whatever the case may be. But that wasn't completely necessary. With Q, R, and PT being parallel to one another, we actually have that angles on the same side of the transversal, interior angles on the same side of the transversal QP are supplementary. So we immediately have that the sum of those two is 180 degrees. And then using this relationship, we can find the value of alpha and beta. Once we have the value of alpha and beta, we just need to make sure we clarify that the sum of the interior angles of a 5-gon is 540 degrees, I think is what it was. So then with alpha and beta and these two known, you can solve for gamma. And speaking of gamma, this is a really random comment that's not necessary in terms of understanding the content, but it's worth sharing in terms of being able to write down what's going on and communicate in that way, right? Writing down the same thing that you're given. Oh, so I got three, yes. Oh, right here. So if I wanted to write gamma, it's a little weird. It looks like a Y, that's for sure. It looks a little bit like an R, and probably the best way to think of it is more like an R. So R you might just write like that, R. A gamma, a couple of things you do. You add a little bit of a line there, and then this vertical portion, you add a very small loop to. So you could go up and then loop, and then there's usually a turn down as well. And that would be, this I would say is a nice looking gamma. If they didn't all look like that, that's fine, but then we're at least attempting to make the gamma. Should look halfway decent there. So these, I guess, interesting tidbit, right? These are all, right? This one, which we also had to work with, they're all Greek letters. So alpha, beta, gamma, delta. These are all lowercase Greek letters. So I like this list that MIT, somebody at MIT has put up for us. You can select what font you're working in to give the various looks that the Greek letters will have, but a lot of the, a lot of the uppercase looks similar to what we have for the, it's not called the English alphabet, is it? Latin alphabet? Sounds right? We'll go with that. And then, so uppercase, lowercase. But this kind of gives a nice list and lets you know what the things are going to look like. Stuff that's used a lot. I mean, alpha, beta, gamma, delta, of course. For those of you that have had, actually, even if you've had just Calc 1 or 2, Calc 1 with me, then, right, they have the epsilon delta definition for limits. So that you might be familiar with. Eta is used a lot. Theta, lambda, for those of you that will be in linear algebra differential equations next semester, lambda you'll see quite a bit. Mu is pretty common. I think eta and mu might be more common in physics. It seems familiar anyway. Xi is not super common because nobody likes to write that down. However, zeta, that one does get used a lot, especially, I think I referenced complex analysis, either in this course or a different course, but when you're working with calculus, having complex variables, they use zeta quite a bit. Pi, of course, is common. Omicron is not. Sigma is very common, a couple different ways to write it. Tau is not super common, but I think that tau holds a numerical value of 6.28, something. Yes, so tau is 2 pi. I don't know why they have both, but whatever. Epsilon is, I've seen it a few places. Phi is common, as is psi, and omega, again, in the physics applications. Omega is very common. So anyway, a bunch of useless information in terms of, like, that doesn't benefit our content, but it's good in terms of you'll see these letters appearing, if not in this math class, in others for sure. So I've taken up quite a bit of our time today. So I'll try to I was going to say I'll try to pause there, but maybe I want to share just a little bit about assignments, sections 4 and 5. And let's see, with that, we could say in 4, we have a fair amount of information. So for example, I'm confident that we all know that on a rhombus, as we have here in number 4, that gamma and alpha have equal angle measure. However, nowhere in this section does it say that they have equal angle measure. So it would be best if you explained why gamma and alpha have the same angle measure. And that can be done with a simple explanation. Right? That can be explained because the diagonals of a rhombus are lines of symmetry. Right, so if EG is a line of symmetry, then this angle and that angle have the same angle measure. Done. Right, so it doesn't take much to explain it. Similarly, right, we can find the angle measure of beta very easily, but then what is the angle measure of this part and this part? Well, there's a couple of different justifications that you could use. You could use that the line of symmetry, or the diagonal FB is a line of symmetry. So you have that angle FED and angle DGF are the same. And then since that and that have the same angle measure, then this and that would have the same angle. So that's one way to go about it. You could also, okay, yeah, so I think I explained that wrong. I just gave a reason as to why this line of symmetry gives that FED and DGF have the same angle measure. You can solve them to show that these have the same angle measure, but that's not, oh yeah, no, that's okay. Anyway, there's lots of different ways to go about it. Just make sure that you're careful about using the actual information that's given. So it could be. Let's see here. I have the answers to that. So diagonals are bisectors of each other is true in any parallelogram. But if we look at the collection of parallelograms, rhombuses are parallelograms, so yes, that is also true. Using this is also important because I found on at least one of the homework problems, I wanted something that was true. I think specifically that situation, I wanted to say that the two pairs of sides were parallel, but a rhombus isn't defined that way. However, this Venn diagram shows us that kites are parallelograms, and so we do have that the opposite sides are parallel. So citing that is perfectly acceptable. The difficult part is remembering what exactly you're told in the section and what you remember from having prior knowledge. So it's a good idea. In my solutions, I cited activity 4.10 several times. I think on almost every problem for this section, because these are nice ways of referring to what properties that these have. So I think I just referred to this activity and this Venn diagram, and that was sufficient for justifications on my responses. But again, the idea is actually, of course, that's what I referenced from this section. I think I referred to section 3 for several things as well, for what sums of angle measures should be, I believe. So just make sure you're thorough with your justifications. Here, and especially in the second section, sections 2 and 3, they said give your explanation so that way someone else in this course could read your solution. And I think that for the most part, what you guys submitted was did satisfy that with the one caveat of your solutions are readable and understandable by someone who understands the material well in the course. So if you wrote it so that way someone who has seen the content, but you need to explain it to them, I used this as my justification or giving it a reference. It's not, all of that detail is not necessary, but I can share with you that I did not have any homework problem that's taken me more than a page. And some of them I'm realizing afterwards that I could do shorter. So even with the justifications, they're not taking a page. They're not long, but okay. But that's what I want to share for now. That's way more than I usually talk in a lecture. So thank you for paying attention. If you do have any questions, let me know, whether it's here now or those of you on Zoom. Just stop by during office hours, set up an appointment, whatever you need to do for us to be able to get together. All right, everyone here in-lecture has left, so we're going to go ahead and call it a day in terms of anything that I might record. So again, if you have any questions, make sure that you email me, stop by during office hours, or schedule an appointment. And make sure you hand in your homework tonight. I'll see you guys soon.